Fallacy.
Planning fallacy. The Denver International Airport opened 16 months late at cost overrun of $2 billion. I've also seen $3. $1 billion asserted. The Eurofighter Typhoon, a joint defense project of several European countries, was delivered 54 months late at a cost of $19 billion instead of $7 billion. The Sydney Opera House may be the most legendary construction overrun of all time. Originally estimated to be completed in 1963 for $7 million, and finally completed in 1973 for $102 million. 1. Are these isolated disasters brought to our attention by selective availability? Are they symptoms of bureaucracy or government incentive failures? Yes, very probably. But there's also a corresponding cognitive bias, replicated in experiments with individual planners. Bueller et al. Asked their students for estimates of when the students thought they would complete their personal academic projects. Too specifically, the researchers asked for estimated times by which the students thought it was 50%, 75%, and 99% probable their personal projects would be done. Would you care to guess how many students finished on or before their estimated 50%, 75%, and 99% probability levels? 13% of subjects finished their project by the time they had assigned a 50% probability level. 19% finished by the time assigned a 75% probability level. And only 45%, less than half, finished by the time of their 99% probability level.
We always think it's going to take this
As
long.
Buller et al. wrote, the results for the 99% probability level are especially striking. Even when asked to make a highly conservative forecast, a prediction that they felt virtually certain that they would fulfill, students' confidence in their time estimates far exceeded their accomplishments. 3. More generally, this phenomenon is known as the planning fallacy. The planning fallacy is that people think they can plan, in order to prove that a group of people are actually worse planners than a random collection of people. People could simply randomly create plans for these groups and have them monitor which people in the groups did better and which groups did worse than chance would predict. This is done all the time in business and other professions, such as on job applications. The exact plan doesn't matter nearly as much as people's guesses. In practice, I don't think people usually have an incentive to assume that the planned event is the probability that their predictions assign it. People take that chance and fail in order to run their prediction anyway. With time projects, some people might show some pessimism, but won't plan on completing by 99% probability. Those who show optimism won't be scared away by pessimistic predictions made by the subject. And many will keep hoping and planning in the face of accumulated bad news until their 50% prediction is indeed reached, thus creating some confidence bias into the result. This may not always work out very well, but I suspect the important result for most people is that even if it fails, then you can stop with your effort when it did not reach 100% by the original rule set instead of just continuing with your plans and possibly dropping into even greater failures. Just as other people that have worked past 50% will similarly stop soon enough and adjust. Delusions of efficiency. Causality science. Causality in physics means something more fundamental than Newtonian. type determinism. If it weren't so, then physics would have a clear-cut cause-effect graph from start to finish. Einstein, and general relativity in particular, treats spacetime as a unifying coordinate system. An observer on Earth is observed by one in Mars and one in Saturn, and it is possible to reduce this fact of perception to the framework of general relativity, otherwise known as the law of mass energy conservation. When we draw a simple space picture on a page, with us at the center and planets moving away at different speeds in different directions, then it looks to our eyes like one specific moving object moves through space containing many other objects that were collapsed by special forces that appear as straight lines extending to different objects on the page. Of course, reality does not have a flat map onto our perception. Our brains do not translate the true nature of space-time into flat images on paper in this way. But this is a simple enough model which we can make work for a very nice communication plan to serve as our logical starting point. The map that we create from space-time is something that appears to us to be three-dimensional in some real physical sense. You can play with it yourself if you ever have the opportunity to travel at some gravitational speed of some planetary distance or velocity. Take it off the desk and find out how it really works for yourself. After all, gravity isn't doing anything more than pointing to identical force poles at any object's surface of reference, an object with its gravitational attraction plus a negative momentum pushes off our direction, or vice versa. When we use words like space, or matter, or motion, we're not usually talking about something three-dimensional. We are talking about a set of vectors on the x, y, and z axis of a regular triangle-shaped three-dimensional figure. For to specify these, we don't use space names such as space or matter, but mathematical functions instead. A vector function, when we have two functions of b together and placed anywhere on an imaginary number field that has vectors as components. The expression ab equals ca can be said to be equivalent to ab equals ba, or ab equals ab plus ba, or equals a plus asterisk. In other words, any linear function can be rewritten using two-dimensional symbols as a vector, whereas we can specify its dot product in 3 dimensions by writing a dot product between two vectors as a dot product between 3 vectors. A plane represents 3 vectors held together on paper, so they cannot be determined by specifying only 3 straight lines in any given plane. Some of these vectors are linear combinations of all of the remaining ones, in the sense that a plus b equals c. Therefore, a vector in 3 dimensions is essentially a linear combination of the vectors which define that plane. When a vector is in any one of the 2, 3 or 4 planes that lie at right angles to one another, we write its projection with a short arrow pointing upwards as p/2x plus p asterisk b equals cx plus c plus it, and with a short arrow pointing to the left we write its projection with a short arrow pointing to the right as p asterisk x equals cx. A plane has a positive angle at right angles if x and I have no common factor. Planes have no other angles that are not right angles. A plane is, therefore, a subset of Euclidean space. 5. A vector, which is a linear combination of all positive linear combinations of two other vectors, is a line that joins any two of its three vertices, even if one is not shown explicitly. E.g., as with a tangent line to the sphere. If the projector of a line P on a plane can be represented as PP1, P2, P3, then the line is tangent to the plane at P1, P2, P3, or just 1, 2, 3 if we choose to write out the components in our system notation as x1, y2, and z3 as a triangle without point P. The point of tangency of the plane is always at a tangent line if the plane and line are independent. The points P1, P2, P3, and 1, 2, 3 are called the vertices of the plane. They are not unique because any line has a finite number of projections to any given plane. In our world of flat vector diagrams, this can be shown as: for every line L with plane P and PP1, P2, P3, we can find a plane W so that L and W intersect along the common line for a point P4, but without line L having the P1, P2, P3, and P4 points in common, in which case line L and plane W intersect at right angles. Such a point P4 can only have the P1, P2, P3, P4 points as the XYZ components of it. This point P4 is not one of the 3-point triangles. Its tangent line points to the right in a right triangle, but line L lies parallel to the y-axis. So, the P1, P2, P3, P4 points are not three separate vectors. They are only vectors that lie along line L because any PP1, P2, P3, P4 point is PP1, P2, P3, P4 point because any PP1, P2, P3, P4 point is PP1, P2, P3, P4 point because any PP1, P2, P3, P4 point is PP1, P2, P3, P4 point because any PP1, P2, P3, P4 point is P1, 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 P2, P3, P4 is PPP1, P2, P3, P4 point 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 is
Alright, I'm going to turn this off and on, and I'm going to turn it off, and then title it again, and I'll be less than a minute.